So let f be a function defined on some interval from a to 0. If they say interval, these are both x values. Correct? If they say interval, that's an xx. That's a domain. Okay? That is not an xy coordinate. So if we're going from a to infinity, so basically greater than a is what it's saying there, right? That's interval notation. Limit as x approaches 0, f of x equals L means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large. So if you want to find out what L is, the answer to this, you could take your function and you could plug in hecka large x values. I keep using hecka, it's my new thing. I made it up. Hecka large. Because we need x is going to infinity, right? So I could start at 1, plug that in, then I could plug in 5, then I could plug in 1,000, then I could plug in 1,000,000, then I could plug in 1,000,000,000, and I'd be getting closer and closer to what my limit would be. Okay, that's all this is saying. Now this one is saying, let f be a function defined on some interval from negative infinity to a, so less than a. Then the limit as x approaches negative infinity of f of x equals L means that values of f of x can be made arbitrarily close to L by taking x sufficiently large negative. So like negative 1,000,000, negative 1,000,000,000, and see what it gets closer to using a table that we did at the very beginning. So definition, the line y equals L is called a horizontal asymptote, which you learned about already, of the curve of y equals f of x. If either the limit as x approaches infinity of f of x equals L or negative infinity. Because remember, if this was your graph from 30-1, where would my horizontal asymptote be at? Let's pretend that's a great line. It would be at, that's a y. It would be at y equals what? Looks like maybe 1, right? Do we agree? Okay. If I'm saying this one, if I'm saying x as it approaches infinity, so that means I'm getting larger x's. If I keep making my x larger and larger and larger and larger and larger, this is about 10. Say I make it be 1,000,000, it's like way the heck down there. What's it going to get closer and closer to every single time? Y equals 1. It's just getting closer and closer to y equals 1, isn't it? Now if I go do this one, which is negative infinity, what's it going to get closer and closer to? As I keep going this way forever, all the x's that way. It's going to get closer and closer to 1. So when you take the limit as x approaches positive infinity or negative infinity, you're actually getting the horizontal asymptote. Okay? We're going to go down here. Example 1. Determine the infinite limits at infinity, and horizontal asymptotes for this. So I'm going to say that this is the graph of f of x. So I want the limit as x approaches negative infinity of f of x. So as I'm approaching really large negative values, what's it getting closer to for my y? So negative infinity is this way, correct? Yeah. Getting closer and closer to what, Elliot? 2. Getting closer and closer and closer to 2, right? Then we do the limit. How would that be negative 1? Okay. All right. Now, as we approach x positive infinity, we are not approaching y infinities here, right? We're approaching x positive infinity. So as I carry on this way for life, what am I going to get closer and closer to? 4. So your asymptotes, horizontal asymptotes, don't have to cross through the entire graph. They can just be following on ends. So this one can have a horizontal asymptote at y equals 2 as I approach negative infinity, and this one can have a horizontal asymptote at y equals 4 as I approach positive infinity. We have only looked at asymptotes on rational graphs, exponentials, and logs, and that asymptote always followed through, right? It went the whole way. They don't have to. All right? Okay, we're going to flip over. So, we need to look at the limit of 1 over x. Okay, can everyone type 1 over x into their calculator? just 1 over x, that's it. All right. Okay, guys. When I put 1 divided by x into my calculator, this table of values, which of those limits is it covering? Look at here. This table of values, I'm inputting 100, 10,000, 100,000. Which one am I approaching? Positive infinity or negative infinity? 100, 10,000, 100,000. Which x value am I going towards? Really large or really large negative? Really large positive or really large negative? Positive. Positive, correct? I'm getting bigger positive. So this table can represent the limit as x approaches positive infinity of 1 over x. Because what am I doing? I'm putting in values and they're getting larger x values, larger x values, larger x values, and I'm getting closer and closer to positive infinity. Positive infinity is a concept. You can't actually get to it. It doesn't stop. Okay? So if I put in 100, second trace value of 100. Now this is the fun thing. If you go second trace value 100 and your calculator gets mad at you, it's because your window is from negative 10 to 10. It can't calculate anything bigger than that. So I'm going to go to my window, and I'm going to make my x minimum be negative 100,000, because I'm going to type it in after this. So I'm going to make my x minimum be negative 100,000, and then my x maximum has to be 100,000. Because you can't do second trace value of what your graph can't see. So you need to make your window fit the data of the table that you're putting in. So your x min needs to be negative 100,000, and your x max on the window be 100. So we change our window because it can't do the value of what it can't see. So I just changed my x's, I don't care about my y's. So now I go second trace value, and I put in 100. And now it actually gives me a value. 0.01. Then I do 10,000. 0.0001. Then I do 100,000. 0.00001. What am I getting closer and closer to? 0, right? So can I say that if ever I have the limit as x approaches infinity and I have 1 over x, can I not just put a 0 in that spot? So this, the limit as x approaches infinity of 1 over x is 0. Guys, what if it was 1 over x squared? It would still be 0. It's just approaching it faster, correct? Because if I put in 1 over x and I put in 100, I'm going 1 divided by 100 and I get 0.001. But what if I went 1 divided by 100 and now it was x squared? It would be 100 squared. So it's going to get to 0 faster, right? So I can also say the limit as x approaches infinity of 1 over x, I can put in 0. If it was the limit as x approaches infinity, this is what your prof will do, 1 over x to the n, it'll be 0. But what could n be? N could be 1, n could be 2, which is going to be faster, n could be 3, it even get to 0 faster, 4, it gets to 0 faster, 5, it would get to 0 faster. What does n have to be? Could it be a decimal? 1.5? Yeah, it would just get there faster. What can't it be? Can't be 0, or it would just go away. And it can't be what else? Negatives. Because if it was x to the negative 1 or x to the negative 2, that would be the same as x squared. Right? Like if I had 1 over x to the negative 2, remember in grade 10 you were taught that you can make a negative exponent by bringing it up? So that's just x squared, right? So I can't have negatives, because that's not the same thing. So if your prof wants to use this, I should use an eraser. If a prof wants to use n, which they will, they'll have to say n is an element of what? Could it be decimals though? Integers are negative. That's not going to be helpful. It has to be 1 to positive infinity. What are those numbers? There's actually no such thing. You have to limit it. You have to say n is an element of the reals, and n has to be greater than 0. right? We can't say natural numbers because there's also decimals involved. All right. Let's look at this one. What if I put in a large negative 100? So I go negative 100. Oh, I get negative 0.01. I put in negative 10,000. 0.0001. Negative 0.000001. So if I approach it from negative infinity, what's it getting closer and closer to? Zero as well, is it not? Press graph. Actually, go zoom 6, because your window's so bad you can't see it right now. Go zoom 6 back to your standard window. You have a graph sitting in front of your face that looks like this. This is a very sketchy graph because I didn't even sketch a point. I literally just drew something randomly. If you drew like this on a test, it'd be bad. I didn't even put a point. I just went, yeah. Okay? So we don't want to do that on a test. But we can do that here because we're talking about it. So as I'm approaching negative infinity, as this graph is approaching negative infinity, what's it getting closer and closer to? 0. And as this graph is approaching positive infinity, what's it getting closer? Come on. What's it getting closer and closer to? 0. That's all this means. Right? That's why. They are approaching 0 on their ends. Yes? Okay. So, if ever I have x approaching infinity or negative infinity, and I can get it to be 1 over x, 2 over x, 3 over x, 4 over x squared, 5 over x cubed, 6 over, just a number over an x, x1, x2, x3, x4, x5, x6, I can instantly replace that with a 0, because that's what it's approaching. So this is how these rules will work. Okay, we're going to evaluate these. I want you to give me the horizontal asymptote of this first one. Do you remember your rules? Anyone? This is going to be y equals what? Are they the same degree? Are they the same degree? If they're the same degree, you can take the leading coefficients, correct? And make a fraction out of them. So what's it going to be? Y equals 3 over 5. We agree? And that was a rule we gave you, possibly. Kyle doesn't remember it and he was with me, so maybe you don't know. All right. But now you've relearned it, so we're good. But how did your teacher give you that rule? Because your teacher gave you that rule because they understand limits. So if I want to find a horizontal asymptote, I just need to make your graph approach infinity or negative infinity. I'm going to make it approach infinity, which is this one. Yes? Now, I told you if something approaches infinity and I can get it to be a number over x, x squared, x cubed, x4, x5, I can turn that into a 0. Because the limit is 1 over x is 0. The limit of 1 over x squared is 0. The limit of 5 over x squared would be 0. Even if I put a 5 up there, it's still going to approach 0. So I need to get these to be in some sort of form that they're over x. So whenever you're doing these rules, what you do is, actually I'm going to rewrite the question. Silly me. So I'm going to go the limit as x approaches infinity. Now, you're going to have a fraction in the numerator and a fraction in the denominator, just so you know. So be prepared. Had to leave yourself a little space. Can I just divide any term by anything? Like this term by 4 and this term by 5 and this term by 2 and just willy-nilly and just the equation stays the same if I just divide it by whatever I randomly want, any term? No. Can I divide every term by the same thing and that's fine? It has to be every single term. If you're going to divide one term by something, you have to do it to every single term. Okay? So what you need to do is you need to, when you're looking for these, when it's the limit is x approaches infinity and you're looking for the horizontal asymptote, what you need to do is you need to divide by the largest exponent. So what's the largest exponent on all these terms? X squared, right? So we're going to divide every single term by x squared. So I'm going to get 3x squared over x squared minus x over x squared minus 2 over x squared. Then I get 5x squared over x squared plus 4x over x squared plus 1 over x squared. My next step is going to be to write the simplified version of that. So this equals the limit as x approaches infinity. Now, what is 3x squared divided by x squared? 3. Because these will cancel. Right? What is x divided by x squared? Yeah, this will become a 1 and this will become an x, right? So I'm going to get 1 over x. That just stays minus 2 over x squared. All over, what happens here? 5x squared divided by x squared. Left with a 5. Plus, this x cancels off that one, 4 over x. Plus 1 over x squared. Now I told you, any term that has a number over x, or a number over x squared, or a number over x cubed, or a number over x4, if I approach infinity or negative infinity, will turn to 0. Will it not? If I take the limit of each of those? So what's going to happen to this 1 over x? It's going to become 0. What about this one? 2 over x squared. 0 even faster. What about this one? 0. What about this one? 0. What's left behind? 3 over 5, the leading coefficients on the x squared. Why? Because those x squareds cancel off. And so you're just left with those numbers behind. And if I take the limit as infinity as I approach 3, it's 3. Because that's just the line y equals 3, right? If I go to infinity forever, it's still going to be 3. And this is the line y equals 5. If I go to infinity, it's still going to be 5. Yes? So that's why the rule works that if the degree of the numerator is the same as the degree of the denominator, you take the leading coefficients of the largest exponents. Because when you do the limit as x approaches infinity of those, you divide by the largest exponent, it's going to cancel off. The rest are all going to be over an x of some sort, and they're going to turn to zeros. And that's why that formula works. So your answer is 3/5. We're bypassing B for a second. If you look at C, what's the degree of the numerator? 2. What's the degree of the denominator? 2. They're the same degree, are they not? You take their leading coefficients, which this was the fanciest way they could make it out so it would be hard for you. They just put it out of order. Okay? So they put it out of order. This one here, what's the leading coefficient of the numerator? -3. What's the leading coefficient of the denominator? So your answer is y equals -3 over 2 is your horizontal asymptote. Correct? Now, using the limit, show me. Why does that work? What are we going to divide each term by? X squared, the largest exponent. All right. So we're going to get the limit as x approaches infinity of -4x over x squared minus 3x squared over x squared plus 6 over x squared all over 2x squared over x squared minus 3x over x squared. I'm going to show you the long convoluted way that this could be written so that it makes a little more sense. So this one here can turn into the limit as x approaches infinity of -4 over x minus 3 plus 6 over x squared over 2 minus 3 over x plus 7 over x squared. Now, how you can actually, I skipped this step, but you can show this big long step. You can actually write the limit as x approaches infinity to every single term. I'm going to show it to you. So you could, that's why these will turn to zeros. I bypassed it, but I'm going to show it to you. So what you could do is you could rewrite this as the limit as x approaches infinity of -4 over x minus the limit as x approaches infinity of 3 plus the limit as x approaches infinity of 6 over x squared all over the limit as x approaches infinity of 2 minus the limit as x approaches infinity of 3 over x plus the limit as x approaches infinity of 7 over x squared. Now I told you, and it only works with infinity or negative infinity, if I have a number over x or a number over x squared or a number over x cubed, those will turn to 0. We proved it above. Yes? So the limit as x approaches infinity of negative 4 over x, well, this becomes 0, right? Minus the limit as x approaches infinity of 3. So I get 0 minus 3. The limit of a constant is just itself. So minus 3. Then this is the limit of 6 over x squared. As I approach infinity, well, that becomes 0 as well. Over a limit of a constant is just that number, 2. Minus the limit as it approaches 3 over x, 0. 7 over x squared to infinity, 0. So I get negative 3 over 2. So you could show it by splitting it up into separate limits the whole way along, if you so choose. Then it would be little limits, like a whole bunch of little limits. Okay? Let's look at B. Is B same degree numerator, same degree denominator? No. Your teacher taught you that if the degree of the numerator is smaller than the degree of the denominator, it's y equals 0 every single time. Well, with limits, we can show why it's actually y equals 0. What is my largest x? It's x to the 1. So I'm going to divide every term by x to the 1. I'm not changing the gain here just because they're different. It's the same rule. So I'm going to do the limit as x approaches infinity of 5 over x all over x minus 3 over x. I didn't change what I'm doing here. If the limit as x approaches infinity and it's polynomials and stuff like that, you still do the same thing, largest exponent, every single time. Okay? Then we write the reduced form. So I get the limit as x approaches infinity of 5 over x all over 1 minus 3 over x. As I approach infinity of a number over x, what does it turn to? 0. So this becomes a 0. This becomes a 0. And so my answer is going to be 0 over 1. What is 0 over 1? 0. When your numerator is a smaller degree than your denominator, you're going to end up always getting it divided by some sort of x. Correct? Because the larger one's going to have it, so it's going to turn to 0 every single time. That's why that rule works. That's why when you're taught it, it works. But we can't explain that to you because you don't even know what a limit is. Okay? And then so this here says, when you evaluate the limit as x approaches infinity of f of x, it is a way to determine the horizontal asymptotes and why the rules taught in math or Yeshwan work. Not just because you have to trust us, which is what we always say. So this one wants us to find the horizontal and vertical asymptotes. These ones most people are pretty good at. If you look, it's your basic rational. We divide by the largest exponent, correct? This one, people forget about. So I'm going to start just because people forget about it. How do I get vertical asymptotes? Vertical asymptotes were easy. How did we get vertical asymptotes? You're just a what? You're whispering, but I actually can't hear what you're whispering. It's just the denominator. It's what it can't equal, correct? Because it's your non-permissible value. Because if it equals that, our denominator is 0, we have to kick it out, right? So the vertical asymptote is easy. So the vertical asymptote is if the denominator doesn't cancel off. If it cancels off, it's a point of discontinuity, or in calculus, it's called a removable discontinuity. Our vertical asymptote is when 3x minus 5 equals 0, 3x equals 5, x equals 5/3. So that's our vertical asymptote. To get our horizontal asymptote, we have to do the limit as x approaches infinity. We agree? That's what I just said right above. If you don't agree, look above, because then you should agree, because that's what I just told you have to do. So if I want the horizontal asymptotes, I have to do the limit as x approaches infinity of the function. So I get square root 2x squared plus 1 over 3x minus 5. So we're going to have to bring our thinking caps. This is not a hard concept, but I lose people. Okay? I have to divide by the largest exponent. Let's look at the bottom. What's the largest exponent for now? X to the 1, correct? Then people want to do x to the 1 up here. But remember, it's under a square root function, yes? So x to the 1 under a square root is what? So if I need something under a square root to equal x, what would it have had to have been under the square root? X squared. Do we not agree? So I'm going to divide, no. So I'm going to divide the bottom by x. He's trying to get you guys rolling. No. I'm just going to slowly close the door on them. No, they're not coming. Why did you get to leave early? Don't you have math right now?
No, I'm in social, but we're done. These guys told me they could leave 10 minutes early, so I left my class. They said they were done at work.
He's getting recorded for prosperity. Okay, you're slowing us down here. Okay. So we have to divide the bottom by x, and anything with a square root is going to have to be divided by x squared, because x squared is the same as x. So I'm dividing the top by x squared, which is x, and dividing bottom by x, which is x, because the top is a square root. So I'm going to get the limit as x approaches infinity of 2x squared over x squared plus 1 over x squared over 3x over x minus 5 over x. Now some people will say, but I have to divide by the same thing. It's just traveling. It's nice to see you. So, when you divide by the square root of x squared, that is x, right? When you divide by x in the bottom, that's x. So we are dividing by x everywhere. The top one's just x squared, which is x. Yes? So I didn't change the rule. We still have to divide every term by the same thing. Square root of x squared just happens to be x. So these cancel off. That one cancels. That one does not cancel. Ignore that. I don't know what I just did. These cancel. That one doesn't. These cancel. And so I'm left with the limit as x approaches infinity of 2 plus 1 over x squared over 3 minus 5 over x. This becomes a 0. This becomes a 0. So what is my answer? Root 2 over 3. That'd be your homework.